Maybe some of you saw it, maybe not. Let's move me out of the way. Okay. So the announcement that was sent, right? If you've all been here since Tuesday, you know the unfortunate news that now our lab sessions are on campus, right? So I posted up a syllabus about that. I was hoping to have everything resolved and could share TA information, but there's at least one TA who's still trying to work out a swap with another. So I can't put up all the stuff yet because it's likely to change. Anyway, once I get that done, then I'll post it. We should have it all done by tomorrow. I'm meeting with everybody tomorrow at like noon, and then after that, I'll post up the results, and that'll be that. Okay? So it's been announced. Do, 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 do. Alrighty. And the other thing, of course, well, let's just do the lecture. Okay, so data lakes, and databases. So what we'll cover talking about data, information systems, where it comes from, where it gets stored, how it gets stored, and different flavors of databases. All right. So this is the closest thing to a single presentation overview of all the stuff we're going to cover. But it's a little bit of intro of, what we're going to be seeing in much more detail in the next few weeks. Okay. So, as you're surely aware, businesses continuously generate data, right? Anytime something happens in the data in the world, the business has to track it. If somebody buys something, right? If somebody does something on the website, somebody opens up a picture or switches to a new page or loads a page and they track how long that page load takes, right? When shipments happen, things get sent out, notifications get sent out, databases have to record that so that you can get a notification from the UPS or Amazon that your shipment has just arrived, right? And anything employees do. This can be short term, this can be long term, right? This could be checking in for the morning at work. It could be tracking to see if somebody's, sitting in a seat or when they've gone through a security checkpoint or, at the end of a project, if the manager updates the skills, right? Oh, so and so worked with, SQL, this particular project. And so we're going to give him an experience rating that says he learned something. All right. So all kinds of stuff like that, how businesses generate data, and it has to be stored somewhere for later use. So basic structure of data is a table, right? A table is just a fancy term for, not that fancy, it's table, but it's a jargony word for a list. All right. So a table just means a list of things called records. So each record is the information you want to keep about a particular thing. And generally, tables keep records of all the same kind of thing, right? So they call that type. So the same type of record. So you might have a table of customers or a table of cities or a table of stores or a table of students, right? Any of those things. Record, of course, representation of some event or thing, and a field or a data field is an attribute of that thing, an attribute of a record. And that can be different depending on what you want to track. For example, maybe for customers, for one application, you're tracking their authentication credentials. So you need to track their email, their password, their backup questions like what was your mother's maiden name or what was the street you lived on in first grade, something like that. Okay. Those could be attributes. Or if you're tracking customers in terms of sales, it might be information like what purchases you've made recently, right? So different tables, different records, different data fields. It's all designed to represent some kind of underlying reality of what the business wants to remember. Cool? Makes sense? I hope. Okay. All right. Now, long term, looking at data management, the whole history of it is basically big, more complicated systems, right? So, once upon a time, very simple systems were enough. If you want to go way back to the foundations of like modern statistics, it's basically when they were building phone lines and they had to bury big, expensive telephone equipment in the ground that if something broke, it was hard to dig up. So they came up with a lot of statistical models around quality control and around predicting, how often things were going to fail and trying to figure that so they wouldn't have to spend too much time digging up broken telephone pieces, right? Because that was a big job back in the day. Anyway, of course, things have gotten a lot more complicated than that. So over the last, X decades. So relational databases are about 50 years old. Relational databases are the plain vanilla databases of the world. So over time, much bigger tables holding many more records, more fields per record, and more data per field. So could give an example like with Google, just over the last 25 years, right? Once upon a time, Google had a very simple model of how it delivered search results. Essentially, it tried to find pages that had all the terms you included, and then it basically looked at how big the site was and how many pages the site had and how many links pointed to the pages on that site. That was pretty much it. That was what they called their page rank model. And so, if you didn't have a lot of user data, because it was in the early days of Google, they didn't know what people were going to do. So that was the data they had to work with. So they started there. And over time, now they track hundreds of different factors about how to deliver search results. So for every page, they look at different components that might be on the page. They look at what sort of text and what combinations. They look at other kinds of pages grouped together on the website. They look at performance issues like how often it's up or, any reports of, bad stuff, malware, whatever from users, things like that. So again, over time, these tables have gotten a lot bigger, a lot more complicated. And a lot of systems now are even working with petabytes of data. So gigabytes, hopefully you all know that. A gigabyte is a billion bytes. Rough numbers. A gigabyte is like a folder full of images, right? Maybe an image is a few megabytes. So if you have several hundred of those, boom, there's a gigabyte. Terabyte, that's about one person's full hard drive these days, right? Maybe you have a bigger uh, drive. Like I think on most of my machines, I have a 1 terabyte. On my more recent one, that's my desktop that's a few years old. I think it's 2 terabytes total. So yeah, but terabytes, that's in the range of single user hard drives. And petabytes, 1,000 terabytes, that's a whole lot of data. You want a data point on that, something around the order of how much image data Facebook gets in a day, right? That's about a petabyte. Maybe they're getting a few petabytes these days. Okay. So when you're dealing with that much data, it's completely unmanageable by humans, right? So give an idea. Imagine if you were using Excel, and in case you didn't know, last I checked, the maximum number of rows you could have in an Excel document was about 1 million. Okay. So Facebook, they have around the order of 3 billion monthly users. And so if Facebook wanted to use ordinary off-the-shelf Excel to track those users, well, first of all, they need a whole lot of memory to do that in, so they wouldn't even be able to do it on one normal machine. But suppose they could, right? Suppose they solved that memory problem and just wanted to do it in ordinary Excel. They need 3,000 pages of worksheets for anything they wanted to do, right? That's 3,000 times 1,000. No, yeah, 3,000 times 1 million is 3 billion. So again, pretty much completely unworkable to try to do that in Excel. Better than doing it by hand. But if you're talking about, a few thousand worksheets, you're not going to get anything done very fast. So all these systems, as they got bigger, right, stuff that humans can't do has to get automated, right? Basically, increase volume, more data that has to be handled, and velocity, more things happening faster. Uh, I just read, I teach a database course a couple hours before this one, and it's a weird textbook. So part of it started being written in the 80s, and the authors, they've just been milking that cash cow for decades without really updating everything that should be updated. So there's like references to going out to rent some videos at Blockbuster and stuff like that in it. Anyway, one of the things there they talk, oh, modern database systems, they're so big. Some databases require thousands or even millions of operations per day, right? And it's like you can look up and see that Google has to process, not just in terms of single operations, but has to process billions of searches per day, each of which entails many database operations. So that's why we say volume, say velocity. These things are really big. Okay. Anyway. Second thing, difference between data and information. This is one of those kind of things that information technology courses like to bring in up front, and then somewhere on the exam, they'll ask you, hey, what's data? What's information? Okay, well, data by itself, that's just basically the numbers or the words, whatever that you're tracking, right? Without any additional context. So data by itself is very often impractical for humans to use. There's a lot of it. You got to read it, got to make sense of it. Imagine if you had a huge list of social security numbers. That's the data's all there. And say you had the list of the numbers and the names, and I don't know, the city and state as well, right? All the information that you need is there. But if somebody asks you the question of, hey, can you compile a list of all of the people who reside in the city of Chicago with social security numbers that end with 1234, right? You have the data there to do it, but it's not really information in the sense that it's not easy to work with, right? Better modes for something like that would be to sort the data by city and state, sort it by last four of social security number, and then if those are the kind of questions you're using that system for, you could answer them very quickly, right? So information is data that's been processed into some kind of much more usable form, right? Typically information gets pulled from a very big pool of data. And users ask for things like single records or subsets or aggregates from it, right? So, for example, suppose I want to look at my credit card statement from, I don't know, December 2025, because I'm concerned that, maybe my kid borrowed my credit card to buy like $200 worth of Robux. Okay. So I go in and I look at my credit card report and I pull that one record, right? That's an example of that. The credit card company obviously has a massive pool of who all did what and sorted into statements by users, but I just pull the one thing that I want. Another thing is a subset, right? So imagine that I need to see, how much money have I been earning every month in the last year? So I go into my payroll stuff at UIC and I download my complete list of payroll stubs, from January to December 2025, right? So a much smaller set of records. Or if I go to Google and I say, hey, give me all the records that what are we talking about here today? That mention trips to Hawaii for less than $5,000, right? And I run a thing on that, and Google sends me a bunch of ideas on that. Okay. And finally, aggregates, right? Imagine if you're looking at data from a store. Obviously, as a store manager, you don't really want to get the entire pool of the entire list of results from the store, right? If you're an individual user, yeah, maybe you want to go to Amazon and you want to check and say, hey, did I buy this particular thing? How much did it cost? But if you're a store manager, you just want to know what product categories have been selling well, what haven't been selling so well, if there have been substantial variations across stores, things like that. So you get aggregates, you get averages, minimums, maximums, stuff like that. Okay. So those are different ways that data can be transformed into information. So there's a lot of data out there, but because there's so much, it has to be processed into information before it's really useful. All right. Now, every information system is designed to hold some particular kind of data, right? You build the system with the intent that it's going to hold lists of ordinary data, like relational data, like customers, just small stuff like text or numbers, things like that. Or it could be really big stuff. It could be photos, it could be video files, which again, ultimately, yes, they are reduced to numbers, but each individual thing is very big and they might have substantially varying sizes, right? So, depending on the kind of stuff you're going to store, different models for storage make a lot more sense. Okay, so all these design choices, if you're storing photos, if you're storing individual small sales transactions, if you're storing documents, which could be a few megabytes, right? Could have a lot of size variation, could be video segment files that are big but maybe fairly standardized. Depending on what you're doing, you're going to pick a different database model for that, as well as, what kind of retrieval is going to be done. Okay. So, and again, eventually we'll talk a whole lot more about all those issues. Now, the two basic kinds of information systems for this are either operational or analytical. And before I talk a whole bunch, I'm just going to draw a picture because I think a picture is a really good way to do this. All right. So here, right in the middle, I'm going to draw a data lake. I'll do yellow for high contrast. Data lake, all right? The big pool of organizational data. Dun, dun, dun. Okay. Now, data arrives at that data lake from all sorts of different operational processes. I'm just going to draw 5 arrows. Get them reasonably well ordered. Okay. So there could be all sorts of processes happening, right? Could be sales, could be customer service, could be web analytics, which is basically tracking what people do on a website, right? Could be supply chain, could be employees, right? Anything that's going on in the system, in the business that the business wants to track is going to generate data, right? We talked about that. These are called operational systems, right? And they're called operational systems because they produce data in the normal course of doing business operations, right? Whatever the work is that your business does, it's going to produce data. Okay, and you have to store that somewhere. And ultimately, it all gets stored in a big data lake. Now, this big data lake can be a lot of hassle to work with. So just like we talked about the case where you have a big list of people with social security numbers and names, and you don't want to have to comb through all that to find what you're looking for, likewise, the data lake is going to have a whole bunch of data from a bunch of different sources in different formats. And it's really hard to comb through all of that. Yeah.
So would a CRM be considered a data lake?
I mean, it depends on how they structure, but generally not. Generally, a CRM, customer relationship management, generally that would be something that feeds into the data lake,
Okay.
right? Or depending on how you use it, it could receive data afterward.
So would you frame it as maybe a component of the data lake and that would kind of just go under like customer service?
Well, let me get to that because we'll talk about how data gets extracted and then processed. Okay, so, and then maybe that will be clear because depends on what aspect you mean, right? There's upstream and downstream aspects to it. Yeah. Okay. So then data lake contents get transformed, right? They get transformed into some more usable format. Like I was talking about the list of social security numbers and users, you might order that. Say, hey, I know these guys are going to do queries based on zip codes or city or state or by last 4 numbers. So I'm going to pre-organize all of this list of data for that. And I'm going to group it into little buckets that I have it kind of already preset that I can immediately pull the things I need. Okay, so stuff like that is what happens in transformation. There's more to transformation than that, but eventually in transformation, you get what's called, I will come back to your CRM thing though. Eventually in transformation, you get what's called, let's still go with blue, still go with yellow. Yellow is good contrast. You still get what's called the data warehouse. Okay, so the data warehouse is all the cleaned data ready for use, right? Whatever your system thinks people are going to need, the data warehouse has it in a friendlier format than that. Okay. And then end users can use systems called data marts. So a data mart, it's a weird word, but that's, that's the word that's actually used out there for it. So data marts are for subsets of the data warehouse contents, like for specific users or applications. All right, so here's where we get back to that CRM thing, right? So let me draw those last few arrows and then we'll be good to go. With some quality arrows. You guys are getting your money's worth today. All right. So if you're talking about customer relationship management, where some end user wants to look up, hey, what's the status of my account? What are they trying to sell to me? What is the business trying to tell me? That's the data mart side there, right? Anything where you're using it, oh, let's generate some emails to send to this user based on what we know about what they bought recently. Okay. That's on this downstream side. But there's the upstream side, which is if you have a customer relationship management application, part of that is seeing how effective it is. So every time that CRM app takes an action, like sending out an email, it also wants to see, did that email result in a sale or a website visit? And that's going to feed new data into the data lake, right? So it's going to be working on both sides there. Yeah. It's in one case, it's an app that delivers data to the data lake. And in another case, it's an app that receives data from it, from the data warehouse. Cool. All right. Cool. Good question. All right. Anything else? This makes sense? All right. So this side is the operational side. And below here, this is the analytical side. All right. These are data for users after the event to understand what happened or plan new actions. Okay, that's typically what analytical systems are. So you want a classic example for them. Operational systems, you go to Amazon, you buy something for a little while the transaction is going on. Amazon has to make that information available to you. So if you want to cancel it, want to modify it while it's being shipped to you, it's easy for you to look up, hey, where's this item in transit? Okay. While that's going on, that data is going to be stored in an operational system that's easy for you to get to after the transaction is done, right? After the thing has been shipped to you, and chances are you're not going to have any inquiries about it. Eventually, it'll be sent to this analytical side where you're not going to look up your actual purchase on this analytical side. That's for Amazon managers to say, hey, I wonder, how much stuff we've been selling in this zip code. And then your sale will be included as part of that. Okay. All right. So this is the basic model of how databases are used. Okay. So again, all that stuff is what we talk about in the next few slides. So data and information systems categorized as operational or analytical. Operational ones for normal business operations. Analytical data regroupings, transformations of operational data, typically used to answer questions, right? Management type questions. Okay. All right. Now, again, operational systems, typically they're going to use the data right away. So whatever it is, right? So if it's for a supply chain application, it's going to say, hey, I got to store information about this shipment, right? Where it is, has it been paid for, stuff like that. If it's about web analytics, I might be tracking live information of what a customer site visitor is doing while they're on the site. Okay. If it's YouTube, for example, I could be tracking, hey, how much of this video have they watched? Are they flipping around a lot? Are the suggestions that I'm giving them getting acted on? Or should I, try to mix up my algorithm a little bit to offer them new suggestions? And have they been on for a long time but idle? And I need to pause the video and say, hey, are you still there? Right? Okay, so operational systems are doing stuff like that. And they tend to be stored in a format that allows very quick single lookups, right? It's for one user doing one thing that you might want to check up on, right? So if it's Amazon, you want to see while the transaction is ongoing, or while your shopping situation is going, you're adding things to your cart, you want that to be real quick. You don't want to have to, dig out that information from some long list and compile it and bring it into something else. You know that most of the time it's just to do a single lookup. So you keep that information there where it's easy to deliver to users. Analytical systems, again, most often used internally for performance questions. In some cases, they are revealed to users, right? One of the big revolutionary things Amazon did like 30 years ago was offering a recommender system to people, right? The people who bought this also bought that, or people who looked at this also looked at that. That's stuff that comes out of an analytical system, right? Because it takes all this data that's been pooled together. But for most uses of analytical data, it's on the manager side, the internal side of the business, right? So typical questions like what's selling well, what are sales trends, answers like what's the long-term value of a given customer or any given action the business might take, things like that. Okay. So again, these kinds of systems are generally not for simple lookups. They typically involve compiling, filtering, whatever, transforming large piles of data, right? So in order for Amazon to answer the question of people who bought this also bought that, they have to look at all the people who bought this, right? And see all the that's that they also bought. So for analytical systems, generally, speed is nice, but if you're having some internal user wait 15, 30 seconds for a report like this, usually that's not a big deal. But part of what made the recommender systems revolutionary for Amazon is they delivered that information to users really fast so it didn't slow down page loads, right? That was a big, big concern. Okay. So that's operational, analytical, all that. We're about halfway through. What's our time situation? Oh, we're good. Questions, thoughts, concerns? Okay. All right. So the next thing, data structure, right? We've talked a little bit about structured and unstructured data. Uh, Basically, for any event, for anything that you're going to record in your database, somebody has to decide what's going to be recorded, right? It could be a finite predefined set of attributes, right? That would be structured data. Or it could be unstructured. So, for example, if you know in advance all the things you want to keep about a customer account, right? Things like first name, last name, email, phone, street address, other stuff, right? But you know exactly what you wanted to keep in those records. And that would be considered structured data because every record has the same set of fields and the fields are pretty manageable. Okay. For example, in the case of a name, there's going to be some variation in length, but it's not going to be crazy. You're not going to have one user whose name is 5 characters long and another whose name is 10 million characters long. Okay. It's all going to be, within the ballpark of similarity. Also, order line items. So an order line is just imagine if you go to, Jewel or Costco or something, and you get your invoice, you get your receipt at the end that has the list of all the things you bought. Each line has a separate product, right? That's an order line, a specific item as part of a purchase. All right. You can also have unstructured data. Unstructured data ultimately has different fields, or it can be considered unstructured if it just doesn't have fields to speak of, or the mass of the data, each record is wildly varying. So, for example, web pages. Web pages don't have an inherent structure. If you wanted to say, well, yeah, a web page is just a bunch of text, okay, to a point that's true, but it's also unstructured because some web pages can be very short and others can be very, 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 very long. Okay. Same thing with emails. If you're storing emails, again, there's a lot of variance in size there. There's also semi-structured data. So with semi-structured data, the big thing there is some field groups, what is that? Same field groups, right? You might have a document that is going to have at least some of the same fields, but some might be different. For example, imagine if you're tracking purchases as documents. So if a purchase happened, with metaphysical certainty that somebody bought at least one thing, right? Otherwise, they just walked out of the store without a purchase. So any purchase is going to have at least one thing. And likewise, there's going to be information about who the customer was, whether they used a credit card or cash, stuff like that. But in terms of the purchases, there's going to be at least one item, but there could be many items, right? So part of it's structured that that these fields are going to be the same. Things like there's going to be a customer, there's going to be a final total amount, stuff like that. But there's also going to be variation that there might be a long list of items or a very short list. So you can't just treat it as a simple structured data problem, but it's not quite as tough to handle as an unstructured data problem. And all of these have different database models associated with them as well. Okay. So we talked about data lakes as well. Operational data gets stored in their original format, right? But eventually all that data gets sent to a combined repository called the data lake, right? That's where all the operational data goes. Because it's different applications generating different kinds of data, there's going to be a mix of types and formats, right? So you can't expect your emails that you're getting sent to have the same format as ordinary purchases, for example. So for end users, it's going to have to be processed in some way. They call that transformation. It's going to have to be transformed into a more user-friendly format so it can be delivered faster and grouped more easily, more consistently, things like that. So the basic process for that is called ETL, which stands for extract, transform, and load. So you extract data from the data lake, you figure what you want to get, you transform it into some proper format to be stored, and then you load it into a data mart that is available for end users. Okay, so ETL. All right, so that completes part of what we've done, part of what we plan to do. So remember, the name of the lecture is data, data lakes, and databases. So we've talked about data, talked about data lakes. Now it's time to talk about databases. Okay, so let's do it. But last call questions? Data lake? All right. So a database is an application that lets end users do a bunch of things with the data, basically retrieve and store data and edit data that's in there. So they can record new events, right? New records. They can modify records that already exist. Like you can go into your online banking account and make a transaction, or you can change your user info, stuff like that. You can delete records in some cases, and you can run queries. Query is a fancy word for a question, right? You ask the database a question and it's going to give you an answer, right? So, for example, you might ask Google, hey, can you show me pages that are about where I can buy Propel powder? And then Google's going to look through all of its massive databases of web pages and offer you some suggestions, probably a bunch of ads. Okay. So running queries. Now, databases can exist independently. You could always build some standalone thing to manage your life if you wanted to. But in the real world, databases are typically integrated with a whole bunch of other systems, right? In most, like even if you're talking about something small, like uh like my dental, the place where I go to get my teeth done, right? My dentist, they have a database there, and it's not huge, right? How many clients can a dental practice have? Probably a few thousand at most, right? But they have that linked up with other systems, right? Payment systems, email notifications, text notifications, appointment software, stuff like that, right? So they do have a database and it's pretty small. And I'm sure once upon a time they just used it for booking appointments. But, these days it's all going to be integrated with a bunch of other things as well. Okay. And of course, a lot of applications will, in fact, pull data from multiple databases. If you want to think about, depending on how your data lake is set up, right? It could, in fact, be that your data lake is effectively multiple. All right, so I'm going to draw some highlights in here. Is effectively multiple databases, right? So, for example, you might have these two sets, and they're different shapes because they've been transformed. And then maybe these are the chunks of data that get loaded into some particular data mart. Okay, so just as you can take data that effectively comes from different databases, of course, you could have two databases externally feeding into the same end user system as well. Logically, it's the same, but the hardware and software are going to be a little different. Yeah. Okay. All right. Now, databases don't magically appear. People have to think about them, have to build them, and make design choices, right? So, big questions are what kind of data are you going to gather? How are you going to store it? How is it going to be grouped within the database? Who gets access? How are they going to access the data? Stuff like that. And they sound like simple questions, And in some cases, they are. They're simple questions with simple answers. But in some cases, they're a lot more complicated, right? Especially if your databases are big, if they're complicated, if they're changeable, right? These are potentially very deceptively simple questions. For example, about 10 years, 10, 15 years ago, Google started shifting from a purely text matching basis for delivering search results to basically a more semantic model where they tried to assess the meaning of words, and making that shift ended up being such a big thing, such a tremendous amount of work. It actually took Google about 2 years to get done, even though it was a really high priority thing for Google. Okay, so again, answering all those kind of questions, figuring out what to do and how to do it in a big organization, a big system of a big organization, that's going to take a while. That's not something that you and a couple of your buddies are going to hammer out in dad's garage over the weekend. Okay? Okay. Next thing, data quality. I like talking about data quality, right? You'll see why in a minute. Ideally, data should be correct and complete and relevant to whatever problem you're trying to solve, right? If, for example, you're trying to answer the question of whether your employees are doing a good job, then just having a list of transactions from your stores isn't going to tell you a whole lot, right? In principle, you might think, well, if my employees are good, sales are going to go up, but it's rarely that simple, right? Yeah. So in practice, data is often imprecise. It may not be accurate enough for what you're looking for. Uh, it may be incomplete. There's plenty of times where people take surveys and they just leave parts of the survey blank. Just today, I started getting a bunch of requests to fill out a survey about the UIC library. And as it happens, I almost never even go into the UIC library. Probably I've done it like a handful of times in the last 15 years. I've gone inside the building. So I really don't have a lot to say about how the current library, overlords are doing there. I just don't know. So if I do go out and fill out that survey, there's going to be a lot of don't know, can't say, right? All right. And of course, data often gets used for unplanned purposes, right? You work with the data you have, not the data you'd like to have. All right. So, for example, student course evaluations, right? This is a classic data quality issue. So, if you take, for example, the evaluations we get here, they're a little better, maybe substantially better than the ones you might see on, say, Rate My Professor. But why is that? Why is the quality higher? Let's talk about that. What do we mean by quality? What do you think the people who designed the course evaluations, what do you think they're trying to get? What information are they trying to learn? Yeah.
I think they're trying to get as much information as possible from the people taking the courses. And I think the way that they do that is continuing to refine, like, the way they questions, the way they ask, kind of like the way they integrate everything. Because over the past couple of years, I see it's been more questions. I feel like they're more in depth. They got a mix of like multiple choice, like strongly agree, strongly disagree, but then they have written as well.
Yeah.
They're trying to pull as much information.
But what are they wanting to learn about? What are they going to use these evaluations for? I mean, I get it. You're not an admin. You're not on the inner circle of this, probably. But what do you think UIC is good? Yeah, go ahead.
Maybe like the effectiveness of the course to see if the
Sure.
student is learning as much as possible from the grades.
Sure. That's the dream, right? That's what they'd like to know. I thought I saw, yeah, go ahead.
Evaluate the quality.
Sure. Look at how well the instructor's doing. Yeah. What else? Ooh, maybe. Yeah, it could. In some places, it is a factor in hiring and promotion and stuff like that. As far as I know, not at UIC anymore because there's been so much shit posting with reviews. But once upon a time, right, pre-COVID, it was definitely looked at. Yeah, I saw some hands. They recap, they took your ideas. Yeah, okay. Yeah, so basically the big thing, they want to look at how instructors are doing, what they think about the courses, are the students happy, right? And some of that information they can get. But here's the issue. I'm going to actually show you because this is some live data that I took. I'll have to actually dig out the files. I think they're on a machine I had that's broken. But several years ago, you can see what I'm doing here. Several years ago, for my own curiosity, I went to rate my professor and I looked up a bunch of data points, right? And if you've used RMP, you know that basically the two factors that matter are quality and difficulty, right? That's what it uses to do its stuff. And I found a big pool of data that basically, let me make one round one and copy it. Well, I was going to say I can make one round one and copy it. Let's fill it in. There we go. Okay. Ooh. Actually, I'll just start doing it in here. Sure, fine. Oh, I hate that it does that. Okay, don't worry, this won't take too long. It'll just take a minute. It's worth the discussion. This little cluster on the bottom that looks like Orion's belt here. And you need about 5 more to make this proper. Okay. So the pool of data I got, and this is very much what it looked like. If you look at this, you're kind of like, hey, that's a big cloud there, right? I'm not getting a whole lot of that. It looks like there's some general downward trend, but beyond that, it's hard to know, right? Fair? Yeah. Well, as it happens, being an insider at UIC, I know a little bit more stuff than, about this domain. And as it happened, I knew that this particular chain of instructors were a few older guys that were really just phoning it in, right? They were kind of done and it showed, right? And there's that. And this guy, this one on top, he was very good at his field and the students really enjoyed taking the course with him and so he got superstar ratings. Everybody else kind of in this middle belt here, right? And this made sense with what I knew about our organization. I said, yeah, okay, this makes sense. And if you look at this, the lines between the groups are very, very similar. And in fact, when I ran it through some statistical analysis, I found that the correlation between quality and difficulty was absurdly precise for such a small data set. You know, in the real world, you never see results this clear. If I had gone and taken this data and looked at like 60 other departments and gotten similar results, I would have published a big paper that said what everyone already knew, that students who post reviews on RMP like easy professors and easy courses, right? Shocking revelation there. Anyway, but this is, I actually crunched these numbers. Now, the problem is, well, number one, to a large extent, reviews on RMP are kind of like having the people that a manager just fired for not showing up for work for weeks write reviews about how good a manager was, right? It's not a great system. And there's no vetting, there's no verification that people who post reviews actually took the course, stuff like that. So at least the ones you do internally at UIC, hopefully they're a pretty good random sample of the class. Hopefully it's not just people who loved it and not just people who hated it. And as a representative, people from the fat part of the bell curve in the middle, hopefully it's like that. I don't know. But again, some of this stuff, yeah, it's not that reliable. So just because somebody wrote something down, does that mean it's accurate? No, of course not, right? I could point to a bunch of comments in my evaluations over the last few years. I'm like, nope, that's a lie. That's a lie. That's a lie. You know? Uh, Anyway, data sources and distribution. There's definitely a trend for, well, what they say about course reviews is that hate is stronger than love, which is that if the average professor is getting like typically getting fours or so on their reviews, and if somebody really hates them, they're going to put in a one and it's going to take 3 5s to balance that out, right? So that sort of thing can skew the results. Are they relevant to student concerns? Interest. I don't know about other professors because we're not supposed to look at each other's course reviews, but I do know I'm really surprised at how focused students are about or at least the ones that leave the written comments, how focused they are about whether the course was easy or hard, whether it was fun or not fun. And they hardly ever mention stuff like, was this course worthwhile? Did it teach something that's worth knowing? So, if you're an administrator and you want to know, is this professor doing a good job? And what you're getting is 70%, is this course easy and are we happy because it's easy? It's not really relevant to that problem. Okay. And finally, changes to data quality over time. Prior to COVID, the reviews were reasonably good. They were reasonably solid, and to obviously there's going to be some variation, but post COVID and post AI, actually, it got to a point even administrators kind of roll their eyes with how bad and well, whatever, how they don't take the course evaluations nearly as seriously as they used to. When I was up for a promotion last about 5 years ago, they had me tabulate all my stuff from the last, X years of teaching. And now they've, within the last few years, they changed it to professors can opt in to including course reviews, but there's no penalty for not doing it because everybody knows they're not super reliable, right? And some people have suggested they should really be renamed student experience surveys, right? To see if students are happy or not, not so much to see if people are doing a good job. All right. So just saying. And data quality issues like that. Yeah, I mean, I have inner knowledge of student course evaluations, but data quality issues like that happen all the time. You have some data. Is it reliable for what you want to do with it? Eh, you do the best you can. Yeah.
I, like the same data we use for two different things, like maybe not for a positive, like evaluating courses and professors, like maybe if there's like budget cuts or something, maybe to let them go, like
Yeah, could be. I mean,
maybe
yeah, I mean, obviously data tends to get used for many, many different things, right? So for example, if you're a store and you want to check foot traffic, that's going to track, be things for like how many cashiers you need to have at different times of the day, when you need to have air conditioning active, how much security you need to have, stuff like that, right? How often you should plan on restocking currency, how much currency you should have in the store. Yeah, sure. I mean, it gets used for different things. And like I said, there's always, I mean, look, if you get a professor that is getting 1.5 out of 5 reviews, what'll probably happen is people and the admins, they'll say, maybe this is something we need to look into, right? And they might send somebody to observe. And if they observe, they might see that the guy's a complete fuck up, or they might just see that the students are like bitter and angry and, shredding him in the reviews, right? So that's probably they're going to take it as a starting point for an evaluation if the reviews are really, really bad. Yeah. I mean, in practice, and any different schools do different things, but at UIC, that's what would happen. Yeah. Anyway, cool. Okay. So now that we're done with all that, we'll talk about database models. So there's two main database models. They're relational ones and non-relational ones. Relational ones, like I said, they're plain vanilla. Non-relational ones, there's some differences we'll get to. So both of these models, they store records in sets called tables, right? A table, again, is a list of records, and a record is a particular thing that you want to track in your database. Okay? Every record in a table has what's called a primary key. A primary key is one or more fields that allow a record to be uniquely identified. Okay? So the point of a primary key is that, for example, suppose you have a table where one field is the user's email name and the second field is the user's password to the website. Okay? Well, you need to be able to say if somebody enters in that email as their ID, then you need to be able to look through that table and see that the password matches the one that's given, right? So there's lots of situations where you need to uniquely identify records. If you have a user, an Amazon customer who wants to check if he bought a particular product, Amazon will look for the particular transaction by a particular customer for a particular thing, right? Depending on how Amazon set up their databases, It might be a set of fields, right? Or it might just be one. They might just bundle it all together into a transaction code somehow that contains elements of those three things. Anyway, so every record in a table has one or more fields that together comprise that primary key that allows records to be uniquely identified. Also, within a table, all records have the same type, right? So remember, list could be a list of customers or a list of products or a list of transactions, whatever. Now, the thing about relational databases is you can build linkages between tables based on common fields, right? Some of that is what you're going to be doing in labs in the next few weeks. Uh, Non-relational databases, they're more flexible about what sort of fields and formats define a type. And generally speaking, you're not guaranteed to have relational possibilities there. So we'll talk a little bit. All right. Like I said, relationships between tables, they let you write queries that involve multiple tables, right? So, for example, no, sorry, we'll build on this one, right? You have a table of customers and a table of zip codes, and we're going to try to set up a relationship. Okay. So, over here, table customers, and you might have the fields last name, first name, email, phone, I don't know, what else? Street address, I guess, and zip code. Okay. And so, you might have here Jones, Fred, email, fj@gmail.com, phone 312, I don't know, 555 1234, street address 123 Main Street, and the zip code, let's say it's 60602. Okay. Now, zip code table, on the other hand, is going to be pretty simple. It's going to have fewer fields because for what we're doing. For a zip code, you want to track the city and state that's affiliated with that zip code, right? So you would have your zip code, and then you would have your city, and then you would have your state. Okay, so for example, you might have a list, I don't know, 61103 from Rockford, Illinois, and 61614 for Peoria, Illinois, and finally 60602 from what I presume is Chicago, Illinois. Okay? So what happens then, you can set up a relationship. You can say this zip code field corresponds to this zip code field in the sense that if this value here is 60602, then I know that it's going to be linked with this stuff. Okay? So that's basically how relational databases work, is you have to have tables where you specify that there is a relationship between two columns, two fields in different tables. And then what happens in a query? So if you want to ask the query, what is the city where Fred Jones lives, right? You can find his zip code, which allows finding in table zip code the city, right? So you just look up, okay, I have this zip code. I know that if I have this zip code, I can find zip code.city. So I look there, boom, it's Chicago. I got it. Okay. Relationships between tables allow linkages between tables to answer those kind of more complicated query questions. Otherwise, you could only ask questions like, what's Fred Jones's email or what's his phone? Because what it would do is go in and say, okay, here's Fred Jones in the database, and then here's those fields, right? But with relations, you can span across tables. You can do more complicated queries. Okay. Now, like I said, relational databases, they're the vanilla model, for anything you're doing database wise. And if you have structured data, the relational model usually works really, really well. right? So typical relational database features, what you'll see, number one, every record in the table will have exactly the same set of fields, like the example I gave you. And that's how it's going to work in Microsoft Access when you do the lab exercises. A given field will have the same format for every record in a table, right? So you specify the format of the field, like it's a number or a text string, and it's so many digits or so many characters long, and that's limit's going to apply to every record in the table, okay? And basically, this helps prevent conflicting data. So, for example, imagine if I really messed stuff up and I tried to somehow set a relationship in this table, but what did I do? I used a 9-digit zip code for this one and a 5-digit for the zip code table, right? Then there'd be a mismatch. I would never find that zip code entry in the zip code table. And the database would say something like city is null because it couldn't find the city in the database for that zip code. Okay, almost done. Hang in there, guys. Okay. So, on the other hand, you have non-relational databases, right? Also commonly known as NoSQL databases. SQL, that stands for Structured Query Language. It's a basic language for writing database statements. NoSQL actually doesn't stand for no, it stands for not only. So it means not only SQL, it means it's not limited to the constraints of ordinary relational databases. So, non-relational databases are not necessarily designed to allow queries involving multiple tables, right? Most often, they're designed for single record lookups or groups of records from a single table. And if that's how your system is going to be set up, you don't need the extra complications of allowing relationships. Okay, so for example, uh, Facebook images, right? If you want to look at somebody, find some images on Facebook, see what photos somebody's posted, you can definitely go to one of your friends' accounts and look in their photos and see all the photos they've posted over whatever stretch of time. But what you can't do on Facebook is run a kind of complicated query where you ask Facebook, hey, show me all the photos from all the users in Chicago that were posted in January 2014, right? Facebook's going to say, sorry, I can't do that. The system's not set up for that. And the reason why it's not set up for that is Facebook's databases are really big. A lot of stuff that doesn't get looked at very often is archived on very slow hardware. And so Facebook says, if we had to do requests like that, it would A, take a really long time to do, or B, we'd have to throw a whole lot of money into a much bigger, faster hardware system to store all that stuff and make it accessible. It's easier to just tell people, nah, Facebook isn't built like that. Okay. So that's one thing that you might do that for. So again, you see there's this kind of trade-off. In some cases, NoSQL databases might be allowing a more efficient storage system or run on cheaper hardware, but the cost is limited capabilities. Or in some cases, they run faster, but they're not guaranteed to be accurate. So you do have cases like eventual consistency. Eventual consistency, you might say, there's some cases where conflicts of data where there's like multiple copies of the same data and they don't match exactly, where that's tolerable, right? So if you're talking about bank accounts, that's usually a really bad idea, right? You want the copies to be the same. But if you're talking about Facebook has different copies of a post somebody made and they're stored at two data centers on opposite ends of the world, and one set has a few people that have liked it from locally there, and the other has a few people that have liked it from the other local data center, then yeah, it's not super important that those be instantly synchronized, right? Eventually, yes, Facebook will coordinate those likes and bring them together, but it's not worth the hassle of, making sure that everything is correct globally to do stuff like Facebook likes, right? It's not going to cost them any money. Anyway, so things like that, things like eventual consistency get enabled, or things like allowing avoiding the constraints of uniform field sizes or uniform field mixes. NoSQL databases get around that. All right. And again, we'll talk a bunch more about that in the coming weeks, but that's just an introduction to the concept, so I don't need to dig super deep. All right. So again, like I said, data lakes, they're receiving data from a bunch of different sources in different formats. So collectively, they have a wide mix of formats, and the entire data lake is going to be considered non-relational for that reason, right? It's just going to have a mix. It's considered unstructured data. So for most business uses, what happens is the contents of the data lake are the raw materials to build usable data marts from. Okay. So for example, with if you had an Amazon product page, right, you're going to have one database that holds the actual product details, the description, the manufacturer, stuff like that. You're going to have other databases that have information about availability, what shipping options are possible, any promotions, user reviews, stuff like that. And all of those things get integrated into a single web page, right? When you go to Amazon, those different databases feed data together to construct that web page for you. All right. So, recap databases, all right, the amount of data that we're dealing with now have gone from big to ridiculous. And so you need database systems, information systems to handle that because there's no way you're doing it up by hand. Okay. Data could be structured, could be unstructured, and either way, they're going to be stored in structures called tables, where each record is going to be a particular thing, and each record will have some fields. Operational systems gather data as part of normal business. Analytical systems take that data afterward, bring it together, transform it, allow it to be used for answering questions. Okay. Data lake is the data source that feeds end user database applications, right? So all of that data from the operational systems goes into the data lake, and then that data lake, its contents get transformed into usable data in the data warehouse that can be then delivered to end users. And finally, databases may be relational, which is typically for structured data, and non-relate or could be non-relational, typically for unstructured or semi-structured data. And we'll have much more to say about all that next week. All right. That's all I got. Questions? All right. Cool. We'll see you next time. Have a good weekend. Yep.